We're going to start talking about some of the gas laws. Remember, we had said in the previous video that gas laws are the relationships between volume, right, the amount of space that it takes up, pressure, the forcefulness of my collisions, more collisions, higher pressure, less collisions, lower pressure, my temperature. We were using temperature as a measure of molecular motion, right? It's a measure of average kinetic energy. Kinetic energy is energy in motion. So we can say higher temperature, the particles are moving with more energy. Lower temperature, the particles are moving with less energy. And then the amount, right? Well, how many moles of gas do I actually have? So we're going to look at three individual laws, and then I'm going to look at the ideal gas law. So 4 laws total that we're going to look at. And our first one is Boyle's law. And Boyle's law looks at the relationship between volume and pressure. So volume, the amount of space that it takes up, and then pressure, the forcefulness of those collisions. So volume, and we are keeping motion, so I'm keeping temperature, and then amount, the number of particles, constant. We should actually add that at constant. Because if you vary more than just those two things, then this relationship doesn't always hold. So at constant temperature and amount. So I have these particles, they're moving around, right? Kinetic molecular theory, they're moving constantly in straight lines. They bang into the walls of the container and with each other, but average energy is remaining constant unless I change the temperature. So they're moving around. If I now decrease the volume, I'm keeping the same number of particles because the amount, n, is staying constant. They're moving at the same speed, right? Because I'm keeping temperature constant. So if I was to compare A to B, right, which one is going to have more collisions? Yeah, right, B, because I put it in a smaller space, right? If you took 10 people and put them in a large room and had them move around, and then you take the same 10 people and put them, let's say, in a small closet and have them move around at the same rate, they're going to bang into each other way more in the closet than they would in that large room, right? If you decrease volume at constant temperature and amount, you're going to increase those collisions. So this relationship is inverse, right? As volume gets smaller, pressure gets bigger, and then vice versa. If I would have started with B and went to A, my pressure would go down as my volume increased. So this is an inverse relationship. Right? As volume increases, let's actually do decrease because that's how I said it first. As volume decreases, the particles will collide more. And this is, of course, keeping amount constant, right? If I took 3 of those particles out, they wouldn't necessarily collide more in a smaller amount of space because there's less of them. So the things that are constant are just as important as the things that I'm varying. I'm very likely to ask you to explain Boyle's law. And when you're explaining it, make sure you talk about the things that are constant too. Otherwise, this inverse relationship doesn't necessarily need to be true. So as volume increases, the particles will collide more as long as they move with the same amount of energy, right? If you took those 10 people again and you put them in that small closet and then they just kind of stood there and bounced in place versus moving around, they probably wouldn't collide more. So this is also important. So as volume decreases, the particles will collide more, so that's higher pressure, as long as they move with the same amount of energy. So Ke for kinetic energy, and and you have the same number of particles. It's kind of worded weird. And then, of course, you could write the opposite. As volume increases, the particles will collide less as long as they're moving with the same amount of energy and you have the same number of particles. So do you be able to describe it? I'm looking for a paragraph similar than that. kind of at like a 130 level, you'd add just to be able to recite the law. Now I want you to be able to explain the law, right? This is one step up. Mathematically, the way we could write it, I could do volume times pressure is equal to K. K is just a constant. It doesn't really matter what it is. It only matters that it's not changing. So if I want V times P to always equal the same number, if one gets bigger, mathematically, the other is going to need to get smaller. So the next one we're going to talk about is Charles' law. And Charles' law is the relationship between temperature and volume, and we're keeping the number of moles at constant, N for number of moles, and pressure. So we're keeping pressure and the number of moles constant. We're looking to see how volume changes as the temperature changes. So what is my relationship between temperature and volume at constant N and P? So volume again is the amount of space that it takes up. So I'm going to have this amount of space. I'm going to put 5 molecules in there. And then they're moving with a certain amount of energy, right? They're at a given temperature. If I was then to increase my temperature, so if I increase my temperature, right, they're going to be moving with more energy. And we can just say moving faster. That's easier to understand, but they're moving with more kinetic energy, so moving faster. I don't want my collisions to increase. Remember P, my pressure, this is my collisions. It's actually forcefulness, but we can think about it as the number of collisions. I'm also not going to take gas out of it or add gas to it, so I'm still going to have 5 particles. So if they start moving faster, I increase temperature, but I don't want them to collide more often, what has to happen to the volume, right? Hopefully you guys are saying it needs to get bigger, right? If they're moving faster and I don't want to collide more, I need to give them more room, right? And then the opposite is true. If I was to have them move slower, and again, I want them to collide with the same amount of collision, same forcefulness as before. So I don't want them to collide less. I don't want them to collide more. I want them to collide the same. So if I slow them down and I want collisions to remain constant, then I have to give them less room to move around in. Otherwise, they would collide less, and we don't want that. So as one goes up, the other goes up. As one goes down, the other goes down. So this is a direct relationship. Right? Boyle's law was inverse. As one went up, the other one's smaller. This one's direct. Right? If the particles were to move with more energy, they would need more room to avoid increasing the collisions. And that's important, right? Because we're keeping pressure constant. If pressure wasn't to remain constant, then who cares, right? Increased temperature, they can bang into each other all they want, and we don't have to change volume. The only reason volume has to change is because we need to keep pressure and the amount constant. Again, if we took moles out, then maybe they wouldn't collide more often. So the things that are constant are just as important as the things that are varying. So if the particles are to move with more energy, they would need more room to avoid increasing collisions as long as the amount stays constant also. Right? If you change the amount, then they don't necessarily need more room either. So as long as the amount stays constant. So direct relationship. And then just like with Boyle's law, be able to explain it to me. I don't want you to just say, well, volume goes down because temperature goes down because they're direct. I want to know why. It's this little paragraph, right? This one, inverse, right? As my volume gets smaller, the particles would collide more because they have less room to move around in, as long as they're not slowing down or we're not removing gas, that sort of thing. mathematically, I could say that volume over temperature is equal to that constant. And again, it doesn't matter what K is, it just matters that it doesn't change. So if my number on the bottom gets bigger, then the number on the top also needs to get bigger, so they're still equal to the same number when I divide them. Right? If it was 2 on the bottom and then 4 on the top, that's equal to 2. And if I was to increase the bottom to 4, and it still needs to be equal to 2, then I also have to increase the top, right? If one gets bigger, the other also has to get bigger. So one over the other is a direct relationship. Avogadro's law is our third individual law. And Avogadro's law is the relationship between volume and amount. So the relationship between the amount of gas, which was N, and the volume. So how much do I have and how much space does it take up? And then of course this is at constant pressure and temperature this time, right? The two things that I'm not varying are held constant. So for this one, right, we're varying the amount, so N, and then the volume. So if I was to increase the amount of gas, but I don't want them to collide more often, and I don't want to slow them down because pressure and temperature are constant, do they need more or less volume, right? Do they need more room? So if I had this amount of space and I had my 5 particles, but then let's say I was to increase it to whatever number that is, 1, 2, 3, 4, 5, 6, 7, to 7 particles, and I don't want them to collide more, right? If I kept the volume the same, pressure would increase. I don't want to slow them down, they're going to need more space. So this is going to be a direct relationship also. So direct relationship. As more gas particles are added, more space is needed to avoid increasing collisions, right? We want pressure to remain constant. If their kinetic energy, average kinetic energy, sorry, that's important, average kinetic energy is constant, right? If you slow them down, they don't necessarily need more space. But if they're going to keep moving with the same amount of energy, and you want pressure to stay constant, if you have more stuff, it needs more room, right? So direct relationship. And mathematically, V over N is equal to that constant. Again, K just, we don't care what it is, we just care that it doesn't change. So if one gets bigger, the other also has to get bigger. The last one that I want to talk about in this video is the ideal gas law. You may have learned in 130, if you had 130, the combined gas law. I don't use that, we don't need it. The ideal gas law is really all that we need. And we'll do examples in the next video, but the ideal gas law, and this is probably the one that you're going to use most often. This equation is on the back of your periodic table. I'm just checking here if you hear some rustling in the background. Yeah, it is. So you don't need to memorize it, but it is a really common equation and it's pretty easy to remember. But it's going to be my pressure times my volume is equal to my number of moles times R, which we'll define here in a minute, times T, which is our temperature. So P is still pressure, V is still volume. N is my number of moles, T is temperature, and then R is my gas constant. So R is my gas constant. And this is on the back of your periodic table. Just be careful because there's 2 versions on there, and we want to use the version that has the gas stuff in it. Like one of it is in terms of joules per mole Kelvin. Joules is the unit of energy. The other one is in terms of liters times atmospheres per mole Kelvin. Liters is a volume unit, and atmospheres is a pressure unit. So you want to use the one that has units for pressure and volume in it, because our equation has pressure and volume in it. So that's how I remember it. So 0.08206. Just want to double check, yeah. Liters times atmospheres over moles multiplied by Kelvin. So that's the units. It's messy, but those are the units. And again, the equation and that constant are on your table. Just make sure you use the right constant. They're written right next to each other. So again, use the correct one. Because of those units though, my pressure needs to be in atmospheres. Because there's atmospheres as part of my gas constant, if our units are going to work out, pressure has to be in atmospheres. V is my volume. Because liters are part of the units of my gas constant, it does need to be in liters. So if you're doing a problem and it's not in liters, we do need to convert it when we're using the ideal gas law. N is the number of moles. It's always going to be moles. So my units are moles. Again, moles are part of my equation. And then temperature needs to be in Kelvin. Our temperature for all of our gas law problems will always need to be in Kelvin. We can't have any negative temperatures in these problems, otherwise it doesn't work out. So temperature in Kelvin, always Kelvin. But again, the units on my gas constant help us remember that, right? Pressures in atmospheres, there's atmospheres. Volume is liters, here's liters. Moles is moles, and then temperatures in Kelvin, here's Kelvin. So again, this is on your periodic table, so you can use those units, which are written down for you guys, to help you remember what the units you need when you plug them into your ideal gas law. And then the other thing that I use the ideal gas law for is I use it to help me remember my gas laws, my other ones. So kind of if I write off to the side here, just so it's all in one spot, remember Boyle's law. That was the relationship between pressure and volume. And we said it was inverse. If one went up, the other went down. So if I look at this equation, these two are on the same side. So if I'm keeping the number of moles and my temperature constant, which we are in Boyle's law, R is a constant. That whole side is constant. So P times V is equal to K, right? If one goes up, the other has to go down. I didn't mean to erase all of that. So R. If we look at Charles' law, that says Charles, believe it or not. That was our relationship between temperature and volume. And then those guys are on opposite sides, right? And those were a direct relationship. So if they're on opposite sides, if one goes up, the other also goes up. And then Avogadro's law, that was the relationship between volume and the number of moles. And again, those two, those are on opposite sides, right? Volume is here, the number of moles is here, the equal sign is between them. So if one goes up, the other also goes up. So you can use this, which again is on your table, you don't have to memorize it, to help you remember these other laws.